Okay, so this is an Amines question. It's 10 marks over a lot of different sections. So work through them all, try to answer them, and then review them when you're done. Starting with part A. Here's part B. Part C. Parts D and E. And part F. Okay, so taking a look through the answers, we've got three infrared spectra here. And before I actually answer it, I'm going to remind you that you've got your data in the data sheet that I would recommend you always refer back to. Now, if I take a look there, we know that one of these is a nitrile. I can see that for a nitrile, I would get a peak at 2220 to 2260, which I've got in A, and it's the only place I've got it, so I can be confident with that answer. If I then look at the amine, NH, I've got one of them that has a peak in the 3.5 to 3,300 to 3,500 range. So my primary amine is C. And it's important to note that in a tertiary amine, you don't have any NH bonds because all of the bonds on the N are to alkyl groups. That's why that doesn't give you a peak in that region. Okay, moving on to part B, three secondary amines that contain 4 carbon atoms per molecule. So, taking a look at them, I've drawn them out in full here. I've got an N with 2 ethyl groups, I have an N with a methyl and a propyl, and I have an N with a methyl, but then I've got the branched propyl coming off there. But I've not got the marks because the question asks for skeletal formula. So I put those down like this, and you can see I'm simply showing lines for where there are bonds to carbons. I'm not including the H's. Here's my final one, and you need all three of those to get 2 marks. Moving on to part C. Primary amines can be prepared by the reaction of haloalkanes with ammonia or by the reduction of nitriles, and you've learnt about both of them. But you have to justify the statement that it's better to prepare primary amines from nitriles. So here's a comparison. And what you need to be aware of with haloalkanes, we've done this with nucleophilic substitution in different parts of the course. It can undergo further substitution, whereas there is no further reaction with nitriles. Moving on to part D, we are drawing the structure of a primary amine with 4 carbon atoms that can't be formed from a nitrile. So what we're interested in here is that a nitrile is always on the end of a carbon chain. Now there are many answers that you can give. I think this is the most straightforward one. I've got my carbon chain of 4 and my NH2 is coming off the second carbon. We then have a question about propylamine, adding it to water. This is about the acidics or more basic properties of amines. We know that they act as bases. When I react them or dissolve them in water, I end up making an OH minus, hence it's basic, and the NH2 becomes an NH3 plus. Now, if I've added universal indicator, I know that I'm not going to have neutral anymore. Basic, I'm going to see that it's turned blue. Moving on to part F, and we have here phenylamine prepared by a process involving the reduction of nitrobenzene using tin and an excess of HCl. It tells you very clearly to use H in square brackets to represent the reducing agent. So I know that I'm starting with C6H5NO2, I know I'm adding H's, and I know I'm making C6H5NH2. Now I've somehow lost 2 oxygens from the left, and they are going to be used to make water. And what I've then got to do to finish it is to balance the hydrogens, and I do that by adding a 6 here. Why would this be an aqueous solution? Phenylamine is insoluble in water. Well, actually, we also know we're doing this in an excess of hydrochloric acid, and we know, with our knowledge from elsewhere, Zwitter ions, etc., we know that NH2 can become NH3+. which can then combine ionically, bond ionically with chloride ions. Essentially, it will become ionic, and because it's ionic, that makes it soluble in water.